Okay, ladies and gentlemen, and so today we're going to express our answers to the a system of equations, whether that's given in table form or in symbolic form here connected with the bracket. So let's go ahead and take a look at this first question. Determine all solutions, and here we're given information in a table. So it looks to me like for the solution to a system where we have tabular data, we're looking to see for a given x coordinate when all of the output y values are the same, right, for each of the equations in the system. And even though I don't know the equations, it looks like that happens in a couple places here. So what's one place where I get my solution, right? What's one place? Megan?
0, 9.
0?
0, 9.
Yeah, absolutely. And so 0, 9 would be a solution. Remember, it's x coordinate, y coordinate. And it looks like the x coordinate 0 produces the same y coordinate in each of the three equations in that system, and that y coordinate is 9. And so 0, 9 would be my solution. Go ahead and raise your hand if you have the same as Megan. 0, 9 is one of them. Keep your hand up if you know another one. What's another solution? Thanks, hands down. Maya? 3, 3. And thank you for expressing that as an ordered pair, x, y. It looks like the x coordinate 3 produces the same output y value in each of the three equations, right? And that y value is 3. And so in this case, 3, 3 is my second solution. Once again, raise your hand if you had both of those. So who had both of those, that's all the solutions. Good job, you guys. A couple other values came close, but didn't produce the same output in all three equations. Therefore, it's not a solution. In order to be a solution to a system, a given x coordinate must produce the same output y value in all of the equations in the system. All right, let's take a look at the second one then. In order to solve the second one, you've got options. And so you can use any of the methods that we talked about over the past couple of weeks. We could solve this by graphing. We could solve it by substitution. We could solve it by linear combinations. We could even make a matrix equation, right, and solve it using inverse matrices on our graphing calculator. However, it looks to me like two of those methods are distinctly better than the others. And so what method do you want to use to solve this one? Right? What method would you like to use to solve this? Blake?
The elimination.
Elimination method. And so you reordered it so you had your x's and y's lined up. And then what did you do after that?
I multiplied the top one by -1 for the y cancel.
Awesome. And so we're going to do Blake's steps, right? All in one fell swoop. We're going to multiply everything in that top equation by a -1. That would give us -2x minus y equals +9. And then, Blake, you left the second equation, right, unmultiplied. Maybe you reordered those so it was lined up. Awesome. So we've got +3x plus y equals 11. Again, that's unchanged. We didn't multiply by anything, but we simply reordered it to line up the x's, line up the y's, line up the equal sign. All right, my favorite step then in the elimination method is adding the two equations together. We've created exact opposites in the y's. Thank you, Blake. So -2x plus 3x is a +1x. -y plus y is no y's. 9 plus 11 is 20. In one fell swoop, we've got x equals 20. Gosh, elimination method is clean, isn't it? After I have one of the values, one of the coordinates of my solution point, I can go back into either of the originals, substitute in that value, x equals 20, and then solve for y. So I'll go ahead and grab this second one. It looks pretty ready to go. And I'll rewrite it y plus 3x equals 11. Except everywhere I see an x, we're not going to put an x. We're going to put 20. So I get y plus 60 equals 11. Subtraction of 60 from both sides yields my y coordinate of the solution point, and I'm getting -49. Yikes, math is hard. Well, it looks to me like my potential solution point is 20, -49. But before I box that, I'm going to go ahead and check in my originals. So let's go ahead and check this ordered pair x, y. I must satisfy each equation in order to be a solution of the overall system. So here I go. 2 times x is 2 times 20 is 40. 40 plus a -49. Does 40 plus -49 equal -9? Yes, so it satisfies the first equation. Let's take a look at the second one. Y is -49 plus 3 times 20 is 60. Does -49 plus 60 equal ?11? Yes, it does. By golly, Winner, winner, chicken dinner, and I bet you waited all spring break just to hear Mr. Fritz say that again upon your return, huh? Totally worth it. Snowstorm aside. Yikes. And so, I'm sorry, you weren't here? Oh, if you traveled away from here, then maybe you avoided that if you went somewhere warm. In any case, 20 comma negative 49 is what we've generated and checked. Raise your hand if you had the same thing before I did. So we had 20 comma negative 49. Way to go, you guys. What questions do you guys have on today's Bellwork? Awesome. Then we're going to go ahead and pass around the stapler. I'm going to pause the recording for us to do our homework check. Okay, so we're going to continue using the process known as linear programming to find the optimal solutions to real-life problems. And this is a great strategy, right, because we can use it to systematically find the best solution, right, the best particular outcome that satisfies the given constraints in the problem situation. So last class, we looked at two different linear programming situations. What I want you to do right now is come with me on a magical mystery tour of the mind. Yes, that's right. I want you to think all the way back before spring break, and we had the Friday off because it was half-day parent-teacher conferences, and then we had the Monday off for possible makeup snow day, and it wasn't. So we're talking 5, 9, 10, 11 days ago. Gosh, 11 days ago plus the B-day. So 12 days ago, we took a look at Aaron, who had his illegal junk food business. He was selling contraband food goodies out of his backpack in the commons, right, to make a little extra dough, if you know what I'm saying. And he smuggled in his Red Hots and his juice boxes, right, in order to solve and find the best combination of Red Hot bags and juice boxes that he should buy each morning on his way to school so that he maximizes his profit. We use this exact approach. And so I want you to think back in the context of Aaron's Red Hots problem. Ready? We identified the variables. We let X be the number of bags of Red Hots and Y be the juice boxes. Step 2, we wrote the constraints as a system of linear inequalities. So by constraints, we're talking about what constrains us in this problem. Within what constraints must we work? Well, he could only carry 40 items in his backpack. So one constraint was the number of juice boxes, Y, plus the number of Red Hot bags, X, right? Together had to be less than or equal to 40 because he could only fit 40 items in his bag. That's one constraint. He also had a cost constraint because he only had $10 each day. And he had Big Bruno, right? Big Bruno needed at least 4 bags of Red Hots every day and 4 juice boxes. And so he had those constraints as well. Then we wrote an objective equation. Your objective equation was your objective. What was the point of the problem? Well, Aaron wanted to maximize profit. So we wrote a profit P equals equation for our objective equation. Next, step 3, we graphed the feasible region, right? That system of linear inequalities. We graphed that system of linear inequalities and shaded the feasible region. We then went ahead and found the coordinates of the vertices. In order to do that, sometimes, right, we could do it by guess and check based on our graph. If we were careful and accurate, we could see where the two boundary lines intersected, right? And then went ahead and tested those points x comma y to see if it satisfied the two boundary line equations. Or we have to use a system of equations, right? You could set those two together like Bellwork number 2 and solve and figure out what the point of intersection is. You're going to have to do both of those things today. Then we went ahead and tested each of those vertices in my objective equation. So we tested those x comma y points in my objective profit equation, and then we went ahead and looked at those results, and we stated our decision. And it looks like, depending upon the cost, right, or I'm sorry, the sale price of those, the bags of Red Hots and the juice boxes, we pick a different combination for him to bring each day. So that's what we did. Then we did the bobblehead question to follow up and continue practicing that. With that, today we're going to go ahead and take a look at Mousetrax Technologies. What? Mousetrax Technologies manufactures video games. And so what you're going to do is work in your team, right? Your team is going to be groups of 3 or 4 students, and you're going to identify the optimal combination of ITO5 models and ITO8 models that your company should produce in order to maximize profit, because they're all about the Benjamins, baby, right? And so we're going to go ahead and we're going to, not yet, but in just a minute, we're going to scooch into our groups, and we're going to earn stamps. Up to 4 activity stamps can be earned. So I want you to take a minute right now, and in your packet, if you flip through, we're going to get circle the stamped eligible items. 1B, little circle around that. 3C, 4B, and 4F are the stamped eligible items. remember when we work together in a group, right? In this case, you're a team working for Mousetrack Technologies to determine the number of video game models you should produce to maximize profit. It's important that you're talking it out, making sure that everybody in your group understands it, right? I wholeheartedly believe that by talking about these problems together and verbalizing it, you're going to understand the concept better and remember it longer. So everybody wins when you guys work together and talk it out. So I want you guys to talk. I encourage you guys to talk. I just want to make sure that you're talking about appropriate things. And so you're not talking about, right, where you went over spring break at this time. Now we're talking about our Mousetrack Technologies problem, and we're using this time now to practice our linear program. I'm going to go ahead and pause the recording, and then we'll outline our groups. Thank you for returning your desk to the regular position. I appreciate that. Let's go ahead and take a look at our Mousetrack Technology activity. So in the beginning, right, we were posed with the task of determining the optimal combination of IT05 models and IT08 models so that we maximize profit. So we were given a couple of different combinations of 05s and 08s, and we saw that some of them produced a profit, like $17,500 if we made 200 05 models, and paired that with 100 08 models, versus 20,000, which was a little bit more money, if we manufactured 100 05 models and 200 08 models. However, it looks like if we picked some combinations, they weren't feasible because they violated one of my constraints, like my assembly constraint, my testing constraint, or my packaging constraint. And so, instead of having to test every single ordered pair in this coordinate plane to determine what's feasible and what produces a profit, we saw that we could get the feasible region using the techniques we've developed over the past several weeks. And so if we were to graph that system of linear inequalities and shade the feasible region, we see my feasible region here is a polygon whose vertices are the critical points. And so I found these critical points to be 400, 0, 0, 400, 0, 0. We got all those kind of for free. The only ones where I had to solve systems were this 200, 300, and the 300, 200. And to do that, we could set the two boundary equations that ran into each other up as its own little system of equations and solve to figure out that point of intersection. So by setting my packaging, right, together with our that's the testing, this should be a 0.6 right here with my assembly, we get the critical point 300, 200, and so on and so forth. All right, so in order to determine the optimal combination, we went ahead and tested those vertices in my objective equation, and we found individual profits as shown. It looks like cruising down here, we get dun, 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 dun. There's our winner chicken dinner, a combination of 200 as my X variable, that's the 05 models, when produced with 300 of my Y variable, that's my 08 model, produced a whopping profit of $32,500. And based on comparing that with my other profits produced from the corners of my polygon, that was the winner. So in summary, we could first define the variables. We let X be the 05 models produced. We let Y be the 08 models produced. Our constraints came from assembly, testing, and packaging. And the associated linear inequalities that represent those in symbolic form are shown. The objective function is my objective. What I'm trying to do in this case, we tried to maximize profit. So we had a profit P equals equation, and I saw everybody and stamped that correctly. You guys did great. Our feasible region, right, are the points where all of our conditions work. So we needed to be less than the assembly constraint, less than the packaging constraint, less than the testing constraint. And so that ended up being that shaded polygon that was a pentagon, right? A pentagon. And the corners of that are the critical points. And we just showed how we tested that in the previous one. You guys did a great job with this activity, and I wanted to say thank you for working together. I appreciate you guys talking out. I overheard some good things. I wanted to outline the assignment for next time. It's only that worksheet, the dance and skate worksheet. So your dance and skate worksheet is your assignment for day 8. And we provided kind of graph paper with you on the back there, so they don't need your own. What questions you guys have about today's activity? Great work, you guys. So no book work tonight. I'm going to go ahead and save the recording.